Good day, everyone. I'm Shandar Bitagle, and I'm here today to talk about concrete chemistry. Now, we have here the objectives of the presentation. We have the definition, history, the use, components, the process, as well as the pros and cons of concrete chemistry. First, let's define what is concrete chemistry. Concrete chemistry is the study of chemical properties and reaction of the material used in the production of concrete, as well as the chemical process that occur within the hardened concrete. It involves understanding the various components of concrete such as cement, aggregates, water, and additives, and how they interact with each other. Uh, some key aspects of concrete chemistry includes the hydration of cement, which is the chemical reaction that causes it to harden and become strong. The role of water in the reaction process, the chemical composition of properties of different types of aggregates, and the effects of various chemical admixture on the properties of concrete. By studying concrete chemistry, researchers and engineers can better understand how to design and produce concrete with specific properties and performance characteristics, such as strength, durability, and workability for various construction applications. Let's proceed to the history of concrete chemistry. The use of concrete dates back to ancient civilizations such as the Egyptians and Romans, who used a form of concrete made from lime, volcanic ash, and other aggregates. However, the chemistry of concrete as we know it today began to develop in early 19th century with the discovery of Portland cement. So who is Joseph Aspdin? In 1824, Joseph Aspdin, a British bricklayer, patented a process for making hydraulic cement by burning limestone and clay together at high temperature. He named this new material Portland cement because of his the remembrance of a type of limestone found on Isle of Portland in England. This discovery marked the beginning of modern concrete chemistry, as Portland cement became the primary binding material used in concrete. So in the following years, researchers continued to study chemical reactions that occurring during the hydration of Portland cement, leading to a better understanding of the factors that influence the strength and durability of concrete. In the early 20th century, the use of reinforced concrete, which combines the strength of concrete with the tensile strength of steel, revolutionized the construction industry. Today, the chemistry of concrete continues to evolve as researchers develop new materials and techniques for producing concrete with improved properties and reduced environmental impact. Advances in concrete chemistry have led to development of high-performance concrete, self-consolidating concrete, and other specialized material components of concrete chemistry. The chemistry of concrete involves several components, including cement, the primary component of concrete, which is made up of calcium silicate and other compounds that undergo hydration to form solid structure of concrete. Next, water, the liquid component that reacts with cement to initiate the hydration process, forming calcium silicate hydrate and calcium hydroxide. The next one is aggregates, the materials that give concrete its bulk and strength, typically made of sand and gravel or crushed stones. These materials do not chemically react with the other components of concrete but contribute to its physical properties. Next is admixture. It can be a chemical admixture, special admixtures that can enhance the properties of concrete, such as corrosion inhibitors, water reducer, and superplasticizers. The next is sand, used in concrete as fine aggregate, and its main function is to fill the voids between coarse aggregates and to provide workability to the concrete mix. Lastly, the air. Concrete can contain a certain amount of air, which can improve its resistance to freeze-thaw cycles and it make more workable. What is concrete chemistry used for? Concrete chemistry has a wide range of practical application in the field construction and civil engineering. Some of the ways in which concrete chemistry is used include improving concrete in strength and durability. By understanding the chemical reaction that take place during the curing and hardening of concrete, researchers and engineers can develop new materials and techniques to improve the strength and durability of concrete. Next, developing new concrete materials. Concrete chemistry is used to develop new materials, such as high-strength concrete, self-healing concrete, and lightweight concrete. These materials can have unique properties that make them ideal for specific construction application. It is also for reducing environmental impact. Concrete production has a significant environmental impact due to carbon emission generated during the manufacturing process. Concrete chemistry is used to develop alternative materials and processes that can reduce the environmental impact of concrete production. It is also includes understanding deterioration mechanism. Concrete is a subject to a wide range of environmental and chemical stresses that can use it to deteriorate over time. Concrete chemistry is used to study the mechanism of deterioration and develop strategies for mitigating the effects of these stresses. And lastly, quality control and testing. Concrete chemistry is used to develop and implement quality control measured to ensure the concrete meets specific performance standards. It is also used to test the properties of concrete in the laboratory and in the field. The process of concrete chemistry. The process of concrete chemistry involves a chemical reaction that occurs between the various components of concrete during the curing process. These reactions are responsible for the formation of hardened matrix that gives concrete its strength and durability. Cement is made by heating a mixture of limestone and clay to very high temperatures, which produces a powder known as clinker. When water is added to cement, a complex series of chemical reactions called hydration occurs. During hydration, the water reacts with the various compounds in cement to form a variety of hydrated calcium silicate compounds. These compounds then begin to crystallize and interlock, creating the hardened matrix that gives concrete its strength and durability. Aggregates, such as sand and gravel, provide bulk and stability to mixture, while chemical admixture are added to control the setting time, workability, and the strength of the mixture. The chemistry of concrete is influenced by various factors such as temperature, humidity, and the composition of mixture. For example, a high temperature can speed up the hydration process and accelerate the hardening time of mixture, while the lower temperature can slow down the process of extending the curing time. Pros and cons of concrete chemistry. Concrete chemistry has both advantages and disadvantages, which I will discuss. Pros: strength and durability. Concrete is a strong, durable material that can withstand heavy loads, weathering, and erosion. It can be used in a wide range of construction applications, from building and bridges to highways and dams. Versatility. Concrete can be formed into a variety of shapes and sizes, making it versatile construction material. It can also be colored or textured to create a range of finishes. Sustainability. Concrete is a locally sourced and low-maintenance material that can be made with recycled content and reused or recycled at the end of its life. Fire resistance. Concrete is non-combustible and does not emit toxic gases when exposed to fire, making it safe construction material. Cons. Carbon footprint. The production of cement, the primary ingredient in concrete, is a significant source of greenhouse gas emissions. Cement production accounts for around 8% of global carbon dioxide emissions. Resource depletion. The production of concrete requires large amount of natural resources, including sand, gravel, and water. As global demand for concrete continue to grow, these resources are becoming increasingly scarce. Energy consumption. The production of concrete requires a significant amount of energy, both in the extraction of raw materials and in the manufacturing process. Lastly, maintenance. Although concrete is durable material, it can be prone to cracking and deterioration over time. Maintenance and repair can be costly and time-consuming. That would be all. Hope you learned something. Thank you.